physicists, welcome to Standard 6.1. So you just watched a video that defined some of the very basics of waves. You talked about longitudinal and transverse waves, periodic and pulse waves. This video is intended to just add a couple of more definitions to your bag of tricks before you do the lab. So on this slide, I've got longitudinal and transverse waves kind of depicted here. And let's just remember what those are. So a transverse wave is a wave where the medium moves perpendicular to the wave motion. Okay, the reason I wanted to point that out was just a little trick that I use to keep track of which ones are which. Perpendicular, if you look at the way that we write that mathematical symbol, if you flip it over, it gives you a capital T. There you go. So again, in a transverse wave, the medium, the material that the wave travels through, travels up and down, okay, whereas the wave itself moves in that direction. Opposite to that, for a longitudinal wave, the medium moves in a direction parallel to the wave motion. So that means that any little piece of this wave, think about it like that slinky that they showed on the video, is going to move in this direction back and forth like that, and the direction of travel is in this direction. Again, similarly, we can say, take a look. Parallel are those two lines that kind of line up, and longitudinal starts with an L and ends with an L. So you can kind of think about those L's as that parallel line. So hopefully that's helpful just to kind of keep those in your brain. Now let's take a look at transverse waves in general and see what features they have. So one set of vocabulary that I want you to know is that transverse waves have places where they go up above and down below this thing called the equilibrium. So this line right here is called the equilibrium. We've used that term a lot before. Equilibrium is basically just where the medium would be if there was no wave disturbing it, okay? So equilibrium. When the wave displaces that medium, it displaces it above and below the equilibrium point, and those 2 points have names. The one above is called a crest, and the one below is called a trough, T-R-O-U-G-H. Now, we don't really need you to be able to distinguish between crests and troughs because it depends on which way the wave is oriented, but I just want you to be familiar with those terms, okay? For a longitudinal wave, the equilibrium is kind of where the wave would be at rest again, or the medium, excuse me, would be at rest if there was no wave going through it. But they do have some specific elements in them as well. There are places like this where the medium is kind of squished together, and those are called compressions. That one kind of makes sense given what we know. But the other one, where they're stretched out right here, is kind of a funny word that you're probably not familiar with, but let me share it with you. It's called a rarefaction, R-A-R-E-F-A-C-T-I-O-N, rarefaction. Probably not a word you're going to use a lot. Maybe you'll win a trivia game with it, but there you go. Okay, so those are kind of the distinguishing features of longitudinal and transverse waves. Both waves have ways that we can measure things as it relates to the wave moving through a medium. The first one is the distance between two common points in a wave. So here from compression to compression, here from crest to crest. It could also be from trough to trough, or any two common points. So you could do this spot on the equilibrium to this one. The reason I point this out is that it's not right here because this distance is the distance for one complete cycle, okay? And this distance is called the wavelength. Okay, the wavelength of the wave. And it's marked with a letter that's from the Greek alphabet. It's the letter lambda. And if you've never seen lambda before, it might be kind of a hard thing to say. So writing it out in Roman letters, it's spelled L-A-M-B-D-A. But lambda is just a measurement. It's a measurement of the length, the distance between two common points, one cycle apart on a wave. Can be a longitudinal wave or a transverse wave. The other measurement that we will use a lot is called the amplitude. And the amplitude is much easier to see on a transverse wave. You can measure it on a longitudinal wave, but we won't do that in this course just because it gets a little bit trickier to do. Amplitude is marked with a capital A, which it seems a little bit more straightforward. And both wavelength and amplitude are measured, they're measured distances. So they're both going to be measured in meters. The amplitude, let me just say also, is the distance between a maximum point of displacement and the equilibrium, okay? And that maximum point on a transverse wave can be above or below that equilibrium point, okay? All right, so that is pretty much the anatomy of the waves. I've got 4 other terms that I want to make sure that you're familiar with before we finish. The first one is period. Period is a measure of time, and it's the time to complete, write that again, looks kind of yucky. One cycle, or the time that it takes for a wave to travel through a complete cycle, okay? Period is marked, or the variable we use is a capital T, which might seem a little bit funny, but we use capital P for power, small p for momentum, so we needed something different. The nice thing about it being marked as T is that that helps us to remember that it is, in fact, a time, something measured in time, and the units are seconds. Frequency is kind of related to period, okay? Where period is the time to complete a cycle, the frequency, or how frequently something happens, we often hear that phrase, is the number of cycles per time. And usually that time is in seconds. Okay. Frequency is marked with a small f, not to be confused with our capital F, our favorite forces. But so it's a small f, and the units are, let's just kind of take a look at it here. It's cycles per second. So we can write that just like that. But the measurement of cycles is just counting, and so it's not an official measurement unit. So you could also just say 1/seconds, or we've got another unit for that, which is hertz, Hz, hertz. Okay. Now, one thing to note here is that period and frequency are really intimately related. Why is that? Well, if we look at period, remember period is time per cycle, and frequency is cycles per time. So if you look carefully here, they are basically opposites of one another, right? And if they're opposites of one another, that means that they're just direct inverse. It's a direct inverse relationship. So period is equal to 1/frequency, or you can write it the other way, that frequency is 1/period. That's an important relationship to know. And that one is on your equation sheet as well. Okay, 2 more words. Here they come. First one is wave speed. So wave speed is literally just like how fast a wave moves through a medium. It's marked with a V, and the units are meters per second. Okay, so the lab that you're going to do next is going to start investigating the wave speed. So I just wanted to make sure you knew that. And in the lab, you're going to be looking at springs, creating transverse waves. And one of the variables that they are going to adjust is the tension. So I just wanted to make sure that you knew what tension was too. It's basically how tight a string or other material is pulled between 2 ends. So if you've ever played a stringed instrument, or maybe you've seen somebody like tuning a guitar or tuning a violin, when they rotate those tuning pegs, they are just changing the tension. All right, there are some basic definitions for you. Enjoy your lab.